Hello to everyone. Welcome to this presentation about meshless numerical simulation of steel connection, application to the T-stub component. The authors are JuanJose Jimenez de Cisneros Fonfría, Giovani Jesus Berrospi, and Victor Cook. Presented by researcher Giovani Jesus Berrospi, Pontificia Universidad Católica del Perú, sección de Ingeniería Mecánica, Grupo de Diseño Mecánico. The structure of the presentation is the following. Objectives, description of the research work, discussion of the results, conclusions, and acknowledgement. The objectives are: the main objective is to expose the Meshless method as an alternative of classic FEM to analyze the T-stub component, in other words, steel connections. Secondary objectives are: identify the Jasper and Berrospi model, develop a Meshless model for reproduce the T-stub behavior, develop a FEM model for reproduce the T-stub behavior, and to compare the results with available experimental data, in other words, the Jasper and Berrospi data. Meshless method. There are many meshless methods, such as the smooth particle hydrodynamics methods or the methods that are based on Galerkin. In this case, we use SimSolid software, a software from Altair. SimSolid is based on the theory of external approximation as an alternative to the classic finite element method. Basically, SimSolid solves a boundary value problem by using energy function. This energy function has the particularity of being infinite outside the boundary and has a finite value in the boundary. Also, in the boundary, the degrees of freedom are infinite. By employing this concept, SimSolid can solve the boundary value problem, and we could find the values of the stresses, strain, and forces. Description of the research work. Identify the Berrospi and Jasper model. Well, as I mentioned before, we didn't have experimental data. Therefore, we employed the data of Jasper and Berrospi. Well, in the Jasper and Berrospi work, they studied two T-stubs, the T-stub T1 and the T-stub T2. You can see here the geometry properties of the two T-stubs. Also, we can find in the table, on the right table on the top, the stresses, the yield stress and the ultimate stress, and the thickness of the flange or arm of the web. Also, we can find the characteristics of the bolts. They are N12, 8.8, and they have the yield stress and the ultimate stress of 893 and 974. Then we can find in the work of Jasper and Berrospi the Constitutive Law of the T-stub T1 and T-stub T2. This is a piecewise linear stress-strain curve, and we employ this curve in the SimSolid. This curve is the engineering curve, not the true law, because SimSolid requires the engineering curve as different. And this is different to the FEM model. Well, the FEM model requires the true stress-strain curve. Meshless model, boundary conditions. In many finite element software, we have the symmetry conditions. Well, in SimSolid, we don't have this symmetry condition. We should employ the sliding constraint. And this sliding constraint is applied to the surface 1, 2, 3, and 4. And to the surface 5 was employed the fixed constraint. And in other side of the wet, we employ a displacement. This displacement was assigned as, for instance, a displacement of 1 millimeter, and the software solves the system and gives us the stresses, strain, and forces. Well, as it was mentioned before, this model was based on that Berrospi and Jasper work. You can see here again the geometry properties of the Jasper and Berrospi work. Contact conditions. Well, we employed 4 types of contact conditions in both models of the meshless software. Well, the first type of contact was the bonding between the nut and the bolt. Then we employed the other bonded contact in between the nut and the washer. And then we employ a separating contact between the washer and the flanges. Then we employ a separating contact between the two flanges, but in a surrounding area, circular surrounding area of the hole. This is the default contact condition of SimSolid, because SimSolid recognizes if there are bolts. Then we employ the sliding contact. This sliding contact is employed between the bolt and the hole of the flanges. This sliding contact does not allow the bodies to touch each other, even when there are relative movements between them. Meshless models simulations. As it was mentioned before, we perform the simulation in a displacement field. One disadvantage of SimSolid is that we cannot get the intermediate steps of a specific simulation. It means that we should perform intermediate simulations of intermediate displacement. Therefore, we perform 15 steps for each simulation of the model. Numerical assessment, Fed model. Well, we developed two Fed models according to Jasper and Burst's investigation. These Fed models employ linear brick elements of the available library of ANSYS. The solid 185 was employed. The friction coefficient of 0.3 between the washer and the flange was used, and also the true constitutive law of the materials was employed in the simulation. Discussion of results. Well, we obtained the stresses in the T-stub and in the bolt for both the T-stub T1 and T-stub T2. We could see in the T-stub T1 the maximum stress was 500 megapascal in the zone near to the fillet radius, and in the bolt was 974 near to the head of the bolt. In the case of the T-stub T2, the maximum stress was around 400 megapascal near to the hole in the flange, and 947 in the bolt. You can see here the force displacement curve for the T-stub T1. We could see that the Fenn model reached with good accuracy the experimental test, and the meshless method has not good enough in the plastic zone. But in the elastic zone, we could see that it could reproduce with good accuracy the stiffness. In the case of the T-stub T2, we could see that the elastic zone, the initial stiffness was reproduced with good accuracy, but in the plastic zone, the results were not good enough, because we could reach a value of around 250 and a displacement of more than 5 millimeters. Well, then we compare the result of this experimental test, the finite element model and the meshless model. We could see that T-stub T1 has a value of 201 for that experimental test. The Fenn model reached a value of 998, and the meshless model reached a value of 256. This could give us a ratio between the test and the meshless model. This ratio is 78% for the T-stub T1, and for T-stub T2, the experimental test reached a value of 210. The Fenn model reached a value of 210. The meshless model reached a value of 279, and the ratio between the test and the meshless was 75%. About the stiffness, we could see the stiffness, the ratio between the stiffness of the meshless and the initial stiffness of the test and the meshless was good enough, because we reached a ratio of 88% and 1% between T-stub T1 and T-stub T2 respectively. The spending time on simulations. Well, we could see that it seems SimSolid employed 46 minutes for the T-stub T1, but this time is for the whole steps, intermediate steps, the 15 simulations, and 57 minutes for the 15 simulations the T-stub T2. Well, the disadvantage of the Fenn model is that we should spend time in the pre-processing. It means in meshing and to calibrate the model. But the time in processing was 15 minutes and 4 minutes for T-stub T1, T-stub T2 respectively. Conclusions. The meshless software has got good agreement in the elastic zone, as we saw before. The stiffness value of 13 and 6% from the experimental stiffness for T-stub T1 and T-stub T2 respectively. However, the accuracy of the simulation in the plastic zone was not good enough to consider that the software could predict the behavior of the connection. This lack of accuracy could have been provoked for the content options of the software. As I mentioned before, the sliding content between the bolt and the hole does not allow the bodies to touch each other if they are a relative displacement. And also, the hole cannot be deformed for the bolt when they touch each other. The software does not allow to modify the contact normal stiffness or the stabilization damping factor. Therefore, only we could calibrate the model, the meshless model, by varying the tangent modulus of the material. The time spent on the simulation on the whole study of T1 and T2 was quite short. You see that was 57 minutes for T1 and 46 minutes for T2. These values expose that the meshless method saves time in the processing. Moreover, the meshless method saves time that is spent in the meshing. You see approximately the time that was spent in meshing in the pre-processing was 2 days. The meshless method could allow the companies to apply the simulation-driven design because the software does not require expertise to use it. It means that we could use the simulations in the beginning of the process of designing a structure, a machine, or a component that we are interested to study. And this software allows to the companies to not require experts in the beginning of the process. The bibliography of this research work is presented here. Thank you. Questions?